For lesson 4-2, it's all on binomial distributions. So the first thing you have to do is be sure you know the definition of what a binomial experiment is, because you can't have a binomial distribution without having the binomial experiment. And that's going to be what we're going to tackle here in this first video, is learning how to look at a stated problem and determine if it is a binomial experiment. So here are the conditions. There's 4 of them. And the first thing that it says is that the experiment has to have a fixed number of trials, where each trial is independent of the other trials. So this is sometimes hard to represent, or hard to understand. So I'm going to give you a few examples. Fixed number of trials. These are examples. And it's certainly a short list, but it might help. So in a problem, they may tell you that you flipped a coin 5 times. So the fact that you flipped the coin 5 times, that's a fixed number of trial. Each time you flipped the coin, that's defined to be a trial. So they told you how many times you flipped the coin, so it's a fixed number. The next one is a surgeon performed 8 surgeries. Okay. A surgeon has 8 surgeries to perform one day. That is a fixed number of trial. Each surgery is considered a trial. You could have 10 people answered a survey. Okay, the 10 people, each person is considered a trial. You only had a fixed number of people. It's not, it's not open. It's not continuing. You're not still gathering your data. There was 10 people that answered the survey. So those are all examples of having a fixed number of trials. So once you determine that you do have a fixed number of trials, you also have to determine that there's only 2 outcomes, and the only 2 outcomes is success or failure. So let's say the fixed number of trials for flipping the coin, you would define success as, and then you get to pick heads or tails. So if success is heads, then tails would be failure. So you only have 2 possible outcomes there. You don't have to have, some people think, oh, well, then I could never use a die because there's 6 outcomes on a die. No, that's not true. It's how you define your event. So your event could be, if you were, let's say you roll a die 3 times. Okay, there's a fixed number of trials. You're only going to roll the die 3 times. And let's say that your event is defined to be landing on a 2. Okay, so there's only 2 outcomes. It either lands on a 2 or it doesn't land on a 2. So see, there's still, even though there's more than 2 outcomes possible when you roll on a die, once you define what success is, then it's either success or it's failure. So you could define this rolling of the die, you could define that to be success, to be landing on an even number. So you either land on an even number and get success, or you don't land on an even number and get success. So it opens it up to a whole lot of things. When I first started teaching this, I somehow managed to make the whole class believe that you could only, do things that had 2 outcomes, like flip a coin. You couldn't draw from a deck of cards, or you couldn't, roll this dice because there was, more than 2 outcomes. But no, there's lots of different events. It's not the number of outcomes. It's not the sample space on the experiment. It's not that. It's what you determine as success or failure. That's what we mean by 2 possible outcomes. So the probability of success is the same for each trial. That's when they talk about right here, where they said each trial is independent. That's what they're talking about right here. They have to be independent in order to make sure that the probability of a second event, we've got a number of trials. So if flipping the coin the second time, the outcome was affected by what I did the first time, then we wouldn't have the same number of the same probability of success each time. So, like for example, another number of flip trials, we're going to draw 5 cards. Okay, we're going to draw 5 cards. Now, that's not enough. That's enough to say that you've got a fixed number of trials, because I'm going to draw 5 cards. So there's 5 cards that are going to be drawn. But before you know whether or not it's going to be independent of each other, I have to tell you whether or not the cards are replaced or not. So think about it for a second. I'll explain it as we get down to this other example here in just a second. But are the cards going to have to be replaced in order for this to work? And the answer is yes, the cards are going to have to be replaced. We're going to draw 5 cards, but we have to have with replacement. And if you don't understand the with replacement right there, when we get down to example number 2, we'll discuss that a little bit more. Okay, so we've talked about the probability of success has to be the same, and then the random variable x counts the number of successful trials. So on your variables here, you've got n, p, q, and x. N is going to stand for the number of trials that you have. So in this problem right here, n would be 5, n would be 8, n would be 10, n would be 3, n would be 5. N's pretty easy to do, the number of trials. P is going to be the probability of success, and that's almost always given. Almost always given. So you're not going to have to calculate this. This is almost always going to be given. Now remember, we only have 2 outcomes. We have success, and then we have failure, which is not success. So these 2 are complements of each other. So if the probability of success, let's say, is 0.3, then that means the probability of failure or not success is going to be 0.7, because there's only 2 outcomes. So the probability has to add to be 1. They're complements of each other. And to find the complement, you always do 1 minus the event. So whatever the probability of success is, the probability of Q, which is not success, or the complement of P, is going to be 1 minus P. So that's usually, that has to be calculated. They almost never give you Q. They almost always give you the value of P. They almost always have to calculate the value of Q. And then X right here is going to represent the number of successes that are possible. So in other words, if I am flipping the coin 5 times, how many times might I experience success? Well, if I flip it 5 times, I could have success 0 times. I could have success only 1 time, or 2 times, or 3 times, or 4 times, or 5 times. If I have 8 surgeries, how many surgeries might be successful? Well, 0 might be successful, or 1 surgery might be successful, or 2 surgeries might be successful, 3, 4, 5, 6, 7, 8. Basically, it's always the same as the number of trials. You just have to stick 0 in there too, because it says it's the same number as trials. You just have to include 0 because you may not have any successes. If my event right here for the fixed number of trials, if I'm interested in drawing red cards, let's say I want to, what's the probability, or I want to calculate something about my event is going to be drawing a red card. So it's either red or it's not. So I have success or I have failure. And I'm either going to be able to draw 0 red cards, or I might draw 1 red card, or I might draw 2 red cards, or I might draw 3 red cards. I might draw 4 red cards, or I might draw 5 red cards. Any of those number of successes is possible. Okay, so those are our variables. So in this first example, it says, first of all, determine if this is a binomial experiment. So we have to go through this checklist right here. So the first thing is, does it have a fixed number of trials? It says a certain surgeon has 85% chance of success. The doctor performs procedure on 8 patients. Did you see this right here? So does it have a fixed number of trials? Yes. It has 8 surgeries. Or 8 patients. He does the procedure on 8 patients. So, so the first item on the checklist is checked. Fixed number of trials. This is fixed number of trials. The second one, there are only 2 possible outcomes. Okay, so we're talking about successful surgeries. So we've got successful and we've got failure. The surgery either worked or the surgery didn't. So that is 2 outcomes. The third one is the probability for each one is exactly the same. So here it says a certain surgical procedure has an 85% chance of success. So, and what happens to the first surgery has no bearing or outcome or no effect whatsoever on the second one. So, P is the same for all. Okay, so that's a check. And the random variable X counts the number of successful trials. Okay, so we've determined that it meets all the criteria. So X could be 0 successes, 1, 2, 3, 4, 5, 6, 7, or 8. The value of N was 8. We've already did that right there. The value of P was given. P is right here, 0.85, and you always write P as a decimal, not as a percent. And then Q is calculated. So Q is calculated 1 minus 0.85. 1 minus 0.85 is 0.15. So if we have an 85% chance of success, then that means we have to have a 15% chance of failure. So this is a probability, this is a binomial experiment because it met all of the criteria. All right, so the next one, I don't know how I'm doing on time.